to address this. And so if I think about not so much specialized circuits, but heterogeneous computing or heterogeneous multiprocessing, you can think of the processor space as having a range of granularities, where on a graphics engine you have many, many, many very, very specialized cores. But they only work for narrow applications that map cleanly to them. And on the other end of the spectrum, but they're very efficient when your software runs well on them. On the other end of the spectrum, you have small numbers of cores that are very general purpose and can run just about anything. But you can't have very many of them, and they're not very efficient. And designs like Intel's Larrabee, which has run into some challenges, we're really trying to bridge a small portion of this space. They were trying to build cores that would run the specialized workloads here on the graphics side very efficiently, but also run heavily multi-threaded MIMD-style programs very, very well also. In some sense, they were trying to pick a point in the space and broaden the range that single part could execute on well, to give them a broader market for both specialized and general purpose workloads. And so the challenge is, can we come up with a design that really covers this entire space? A design that's agile and can move dynamically along points on the space. So when you have certain kind of workloads, you adapt and provide the level of specialization that workload needs. And then when you get a different workload, you dynamically move to a different point in the space and run something else. So that's what I see for the silicon as the major design challenge of our time. And so we have one stab at that based on something called edge architectures that I will define in a moment. And I've been working on this stuff for a long time. In my previous job, we built an advanced processor based on these ideas, a second-generation design, and now in my research group, we have a third-generation design called E2 that's really trying to tackle these. So in just a few minutes I have remaining, I'll give you a very quick overall overview of the key ideas and then conclude. And so an edge architecture, which stands for explicit data graph execution, raises the level of abstraction of computation away from individual instructions to large groups of instructions. So what I execute on a processor core is no longer instruction by instruction, but block of instructions by block of instructions. In some sense, treating a block of instructions as a configuration that I'm going to execute as a single unit. And so what we do is we create a data flow block of executions where these are individual instructions connected by data flow arcs. This instruction produces a value that these instructions consume, and then we execute this with atomic and transactional semantics. You fetch the whole thing at once, and you execute it, and then you commit the whole thing at once. And what this allows you to do is to amortize the overhead of executing computation over a much larger group of instructions. You do one branch prediction or one set of control operations, and you get up to 128 instructions with a single operation, as opposed to managing and treating lots and lots of little instructions all flowing around your pipeline. And so in this design, you can pull some number of these instructions, of these blocks of instructions into a window, and then carve this up into slices where this is your execution substrate, and this is where you buffer your operands, and you're streaming these blocks across an execution pipeline, spending most of the energy doing the execution rather than doing the bookkeeping that a conventional out-of-order processor would require. And so the goal here is to be able to execute general code very efficiently, but with much less bookkeeping and overhead than a conventional processor, therefore running with less energy. And one of the ways that we do that is by taking a number of cores. In this example, I've shown you 32 cores in this array. Each one of these represents one of these things. And you map one of these blocks of instructions to a core. This might be block 0. And then you map a second block from that processor thread to a second core, block 1, and then block 2 and block 3. And so in some sense, these cores are cooperating to run a single thread of execution that the software is unaware of. The programmer writes one thread, and then a number of cores work together to accelerate that thread. So what this allows you to do is to dynamically choose how many cores will run each thread. So I could imagine a lightweight, multi-core design with 32 processors, and each of these cores are dual issue with 4 or 8 vector lanes. But let's just talk about the dual issue. So if each of these cores is dual issue, I can marshal these cores together to run one very important thread, effectively giving us one monster processor that's 32 instruction issue wide. And then this group of 4 cores is running a separate thread with an 8 issue processor. And then these cores over here might each be running one thread. And then at any point, I can take an interrupt and change the configuration, changing to a new heterogeneous configuration, running more threads or fewer threads with larger and smaller cores. So in some sense, this is dynamic heterogeneity. And so at any point, I can pick the configuration and specialize it to match the needs of the software at that moment, getting much more efficiency than I would if this was a fixed organization that all software had to map onto rigidly. And so since I'm running a little bit behind, what I might do here, rather than going through all of this, is just jump ahead to my conclusions. But I'd be happy to talk to people offline about this set of ideas. And let me just flip through these last couple. Okay, so in terms of, oops, my last animation gone. So I would summarize my talk by saying that we've looked and thought very deeply about what's happening in the cloud space and what's happening in the client space, and what sort of user models and what sort of types of computation will the two of them put together provide with all of these trends that I've described and that you all see every day. And we believe that a candidate model for this next 5th wave of computing is continuous computing, where you are always connected to rich services and you are always having services delivered to you. But to realize this vision, we have to keep expanding on both the capabilities of the clients, more computation at better energy efficiency, and the data centers, larger services, more services with more users, and high energy efficiency as well. And the challenges posed by silicon scaling and the potential end of Moore's law, or certainly the end of Dennard scaling of transistors, as I showed you, is a serious threat that may prevent us from moving to this next wave of computing. And to overcome this customization conundrum that I described, these continuous experiences will need to be co-designed with the clients and the clouds to pull out the efficiencies we need to make these services work. So this will necessitate an even closer working relationship, for example, between Microsoft and its partners to make this whole ecosystem work and get the efficiencies we need to lead us to a 5th wave of computing. There's enormous opportunity here, and certainly I look forward to working with many of you here in Taiwan in particular to solve these challenges in the years ahead. So thank you for your attention and for listening to my talk.
Thank you very much, Mr. Berger, for joining us today. Since we have about 5 minutes left, we would like to open the floor for questions. We have about 5 minutes for 1 or 2 questions. 各位在场的来宾，我们还有大概5分钟的时间，在我们中午的休息时间结束之前，大概有时间给在场的贵宾能够来提出1个或者是2个的问题。所以，针对于刚刚第2位讲者 Berger 先生他所提出的这些演讲的内容，如果您有问题的话，请您先行举手。我们现场有工作人员手上持着麦克风，我们先把麦克风拿到这一位先生这边。我们请您发言的时候务必对着麦克风发言。
Doug, is the fundamental problem is that the programming model is still volume-based? So you try to map a linear programming model into something that's massively parallel. So last time the trial was epic on Itanian. It wasn't with the software-directed predicates. It still wouldn't be able to solve the problem.
So that's an excellent question. From somebody, I think, with a very deep understanding of these challenges. The the model that I described at the end of this talk and was not able to, obviously, to spend enough time on does not change the programming model fundamentally. You still can run C or C++ code and compile it down to single threads. What this does do, though, is to give you a substrate that if you have threads you can find, you can exploit them on the hardware more efficiently. And if you don't, you have an option of merging these cores together transparently to the application and running faster. So in some sense, the architecture doesn't take a position on how the programmer should program. The architecture just tries to run whatever the program gives it as efficiently as possible. And obviously, I think as you were implying, if you can take the programmer and make them generate different kinds of code, you may be able to run that more efficiently. But the programming problem is so hard that we just decided to let somebody else work on that problem.
Well, the architectural approach is basically transform a computational problem into a communication problem.
Yes.
Right?
Yes.
So you can't guarantee your solution set is more optimal. And sooner or later, there's a crossover point that once your communication overhead gets so big and you have so many bubbles in your pipeline, you're going to end up become less efficient. Right?
Yes. So certainly, as you grow the number of cores collaborating on a single thread, communication starts to dominate, and it reaches a threshold at some point at which your energy efficiency and your performance starts to go down. I mean, our early experiments actually show that about 8 cores works well on sort of control-bound code. So that buys us some time, but it's no magic bullet. Nothing scales forever. We're just playing we're playing a lot of one-time tricks to try to get us to our retirement. Thank you for the excellent question, by the way.
那我们现在接受下一个问题 We will now take the next question. 各位贵宾有疑问的话呢，请您举手，我们现场的工作人员会把麦克风递给您。那也请你务必的要使用麦克风来发问。
People talk about IPv6 for probably 10 years. Do you think when is that going to happen? And then when that happens, will home user move away from cloud computing because you can connect to my netbook, my phone, I can connect to my home PC without going through third-party, P2P servers. So
That's an excellent question. I don't have a personal opinion on when V6 will happen. That's outside of my area and not a question that I've considered. But I do believe that even when that happens, it will be very hard to move away from the cloud as we see it, simply because there is so much data there that is useful for generating interesting services. And I view, you could imagine that on your PC, there are models that will mine your data and learn the things and generate the models about you that you need to generate. But there's tremendous value in coupling those models to public models about everybody that get generated. And so I think you'll still want the cloud because you really need both to generate really very, very valuable services. So I see the cloud as only getting more powerful, not less over time, even with V6. But that's the fun of research. You can always be wrong and not accountable.
好的，那我们再接受下一位贵宾的发问。We'll take the next question now. 如果你有任何的问题的话呢，也请你能够把握这个宝贵的机会。有问题的贵宾，也请您能够举手，我们现场有工作人员会把麦克风交到您的手上。是否还有任何的问题呢 ？It seems that that's it for now.
Thank you very much.
Thank you for joining us, Mr. Berger. 我们是不是再次以热烈的掌声来谢谢 Mr. Berger 为我们带来精彩的回答？